because I've already done that today. And today Paul is now going to talk about permeable reactive barriers. So I'm just going to turn it right on over to you. Folks, welcome back in. Thank you, Paul.
Welcome back, folks. Did anybody eat very much? No, if anybody wants to get coffee, I get it. Get your coffee, get your cookies. I teach a 3-hour night class, so I have mass amounts of sugar and candy on the front. Like, come get it anytime you need it. Even for the next 40 minutes, you need a cookie. Get a cookie. All right. So we're going to talk for the next bit about permeable reactive barriers. PRBs is the common acronym, and we'll go through what that is, and thinking about what are PRBs, what are they, and how they can be implemented for groundwater and soil remediation. So, by definition, PRB is a continuous in situ permeable treatment zone that's designed to intercept and remediate a contaminant flow. And that treatment can be various processes. It could be a physical, chemical, biological process with that. And looking at, we've got some kind of source, we've got a groundwater plume, we've created this PRB, which we want to be that line in the soil, where on the other side of the PRB, the groundwater is treated and there's no, or if not very little contamination flowing through there. So just spending a few moments on each of these three words. Permeable reactive barrier, which would make the acronym of PRB, which I'll really use plenty going forward. It's permeable. This is a passive treatment where contaminants in groundwater are flowing. So if the contaminants are flowing this way, and if the PRB is where I'm standing, they come in, the PRB is waiting for them, and then the treatment happens within the PRB such that the cleaner groundwater, it continues to go down gradient. So groundwater is flowing through that, and by wanting the groundwater, the contaminated groundwater to flow into the barrier, we want it to be as permeable, if not more permeable, than the surrounding soil itself. Because if the PRB or the reagents that you're adding, you're reducing the permeability, now your contaminated groundwater is going to flow over, around, under, or just not entirely to the extent that we want. So there's the permeable component. It's reactive. There is some process going on that is reacting with the contaminants, and we'll talk about what those different reaction processes are, such that the contaminants are groundwater within that barrier. And it's a barrier. We're looking to, again, create that line where contaminants are prevented from migrating beyond that point. So they're your permeable reactive barrier. And depending on what our contaminant is, and what we're also where it is, depth and the like, we'll talk about this. There are different reagents that can be applied for PRB, but there's some common themes, common characteristics that all PRB reagents should have. Most importantly, it needs to be persistent. We want to have a PRB that's going to have a long lifetime, years, and such that we can put that barrier in place and let it continue to react. Ideally, your reagents have very low mobility or are not mobile at all. So if we're going to place them here, we want them to stay here because this is where the barrier is. We don't want to inject something that is going to migrate, and we injected it here, and then the reagents after some period of time are over here. Now we've diluted our barrier, we've thinned our barrier, we've reduced the lifetime of our barrier. As I said, permeability is really important. We don't want to be reducing the permeability. We want the permeability to be unchanged. If not, there's ways we can make it even slightly higher. Reagents for PRBs can be solids or liquids, and we'll look at some of those. But also, it can be a gas as well. We think about like a storage curtain, and I'll show an example of that. That can create a permeable reactive barrier. It also can be electrochemical. I was involved in a project as a pilot test earlier this year, where we're using an e-redox technology to create essentially a fence line, where as chlorinated VOCs move through that, but it does meet the definition of it's permeable, it's a reactive, and it's a barrier. Yeah, I'll let you move on. That's fine. Yeah.
Oh yeah.
Just for.
Is it on a bunch of them?
Which of the font changed?
Oh, that did not bother. All right. All right. So I'll just talk through this. That's fine. So there's many different contaminants that are applicable for PRBs. And some of our common organic contaminants, some of our common inorganic contaminants. But first, I'll start over on the right side with these color boxes, and the boxes shifted here. So the green contaminants are the PRB is undergoing attenuation, which this is where you're actually reducing the contaminant mass. It can be actual degradation, oxidation, transformation into a different chemical, but this is an irreversible process. There are other contaminants that are, and the PRB is going to enhance retardation. This is the PRB removing the contaminant from the groundwater. It's removing it from the mobile form. It may be precipitation. It could be partitioning, sorption onto a reagent in the barrier, but these are reversible processes. So we'll talk through, if we go backwards from 1,4-dioxane upwards, if you're looking at the PDF that's online, they will be highlighted green. These are organic contaminants where the PRB can enhance attenuation and actually reduce the contaminant mass in the subsurface as the groundwater flows into the barrier. And then for inorganics, nitrate falls into that category. And I'll talk about nitrate in several slides, and we'll talk about that one. And then PFAS, and then various metals, arsenic, radionuclides should be highlighted yellow if you're looking at the PDF slides on the NEWMOA website. So just a reminder, all these slides are available. It's all good. So these are PRBs can remove these contaminants from the groundwater, but they're not removing them from the system. The mass of the contamination is still there. So as I said, there's different processes that barriers use to be reactive to remove the contaminant. There are chemically reactive reagents. So for an example of chemical oxidation, Brad talked about potassium persulfate earlier. This is one of the longer lasting oxidants. It's a version of persulfate that has lower solubility and can persist within a barrier for maybe 1 year in the shortest, but I've seen 2 to 3 years, which is nice to have a long lasting oxidation barrier. It's one of the typically chemical oxidants are shorter lived. So to be able to have a persulfate reactive barrier is a great tool in the toolbox. It can be chemical reduction. Zero valent iron is one of the more common chemical reductants used in barriers. The iron can come in different sizes, which have different surface area and also different longevity. If we look back to some of the ITRC guidance documents, these were even created in 2010, 2011. They were tracking the ZVI PRBs that were already in the ground 10 to 15 years and still working. So really that checks the box for persistence. Another chemical reactive reagent could be something for pH adjustment. Many metals, just by adjusting the pH, often slightly higher, can enhance precipitation of metals. So the groundwater may have certain metals flowing into the barrier. There's a pH adjustment going on, and then the metals basically precipitate in the barrier and do not continue to flow on beyond that barrier point. And ground up limestone is one example of that. There's different reagents that can enhance biodegradation within a PRB. And these and that also can be whether it's anaerobic bioremediation or aerobic bioremediation, like Alana talked about earlier. So for anaerobic bioremediation, there's some solid substrates that are available that are commonly used. Wood chips, mulch. Sometimes the wood chips and the mulch can be combined with a little bit of gravel to give it some consistency, but that also really increases the permeability, such that we get increased flow into our barrier because it's actually higher hydraulic connectivity than the surrounding soils. There's various liquid carbon substrates that Alana talked about. We want ones that are going to be longer lasting. They've also vegetable lecithins and the like, which are going to have persistence in the ground and enhance reductive dechlorination or other anaerobic bioremediation for years. I've seen sites where long-lasting carbon substrates can continue to be working 4, 5, 6 years after injection. For aerobic bioremediation, one example would be oxygen-releasing compounds, maybe not 3 or 4 years, but at least a year, sometimes longer. And so there's also, these can be applied either as a trench or within an injection to create an aerobic environment. And then also for bioremediation, as I mentioned, biospargent, gas spargent, either with air or oxygen for aerobic bioremediation, methane or propane or butane for anaerobic bioremediation, or maybe a combination for some kind of co-metabolic bioremediation as well. And then there's various sorbents. These are looking to partition the groundwater contaminant in the barrier itself. Again, so the contaminants come in, contaminants don't leave. And so there's activated carbon is one of the more common ones, and this can be granular activated carbon, powder activated carbon, colloidal carbon is another example. When creating a PRB, the objective is to have a carbon that is not going to be mobile, and it's going to be long lasting, long lifetime. Some of these barriers can have years, if not decades, if they're well designed, and with the right amount of carbon. The zeolite, which are aluminosilicate minerals, used on various radionuclide and other metal projects. There's modified clays, and there's also combinations of activated carbon and clay minerals as well. There was a presentation at the AHS conference at Amherst last month, where there was a pilot study of looking at activated carbon clay mineral injection as a sorption PRB for PFAS. So the next bit of the slide is going to be more on kind of as we plan for our PRBs, and planning for them as well as designing for them, and what conditions are favorable for them. So one of the biggest questions is, well, where do you put your PRB? And the most important part of that is you want to locate it in a location where you're going to reduce the contaminant concentration and notably the flux in order to support attaining your remedial goal. Reminder that your flux is the mass of chemical flowing past a surface area, in this case the PRB, over a period of time, and it's generally the product of your flow multiplied by your concentration. Ideally, you want your PRB to be perpendicular to groundwater flow, or at least near perpendicular, because you want the groundwater is going to be coming in, and so you want to be able to cut that off. If you have a shorter PRB, it's much more important to be perpendicular to groundwater compared to a longer PRB. So if you have a longer PRB, the groundwater flow path is going to flow through that somewhere. But if you have a shorter PRB, you have a higher likelihood of that your higher concentrations may actually flow around them or just not be located in order to capture them. And with some of the access and land usage is really important. This slide here on the bottom here, I just so that I mentioned nitrate earlier. I'm gonna this was a site, a community on Cape Cod. So this PRB and some of this talk for me, it's coming full circle. Just that PRBs have become a potential tool for removing nitrate when there's large nitrate plumes in places like Cape Cod and Eastern Long Island, where 80% plus or minus of the wastewater is going to septic systems. That has happened over decades and decades, large nitrate plumes. I was first starting to get involved with nitrate PRBs as a tool about 10 years ago. But but I had been involved in PRBs for chlorinated VOCs and other contaminants for another 10 years before that. So there were a lot of lessons for the nitrate PRBs that we could take from the hazardous waste side of the remediation side. But a lot of the folks involved in the nitrate plumes were more historically in terms of municipal government and wastewater. So it was a bit new to them. So we had to demonstrate through some bench scale testing and some pilot testing that these PRBs could be effective for nitrate. So as a result, there was a lot of good studies and thoughtful site characterization on some of these nitrate sites. And because of that experience that I've had over the last 10 years, it's nice to bring that back into a PRB session for remediation PRBs, and taking some of those best practices that have been happening for nitrate and showing them within our remediation industry. So in particular, going back to the flux, this community was looking at several different locations for at least a demonstration test. They were looking at about 100 to 150 foot PRB demonstration test, where to put that. They had plumes all over their town, going into several different surface water bodies. So what we did at the time was we installed monitoring wells, we looked at the hydraulic connectivity, we estimated groundwater seepage velocity, got concentrations, and then came up with a flux estimate for each of those PRBs. And we can see these 3 locations had significantly higher flux than these other 4 locations. So that helped us to screen out these 4 locations. And then we went back to these 3 locations and started looking at what was our access like, what was the land usage, and where could we put a PRB that was perpendicular, near perpendicular to groundwater flow, as well as have enough space to have a monitoring well network to appropriately evaluate the performance of our demonstration test. And that's also important. What are your down gradient features? How close was the PRB going to be a potable well, to a stream, to another surface water body? So bringing this all together and trying to figure out where we locate our PRB. PRB placement also has a lot to do with what is your treatment objective. Are we looking to cut off a source area and the higher concentration that prevent a expanding of that plume? Or are we looking to protect some sensitive receptor, whether it's a well, whether it's a stream, whether it's an off-site property line? PRBs can be placed closer to your source, mid-plume, further down plume, but the location has a lot to do with what is your objective. I just want to take a quick moment of distinguishing between a PRB and an injection or remediation transect. A transect, where I distinguish it, it's a line of injection points for a mobile reagent. So in this case, maybe we're not changing the permeability, but we're not creating a barrier. So this is an example where this project has not gone yet, but we have a building here. Through historic manufacturing processes, there's a fairly sizable TCE plume inside that building. But because of the activities in the building, there is not access to actively do remediation inside the building. So one of the alternatives being considered is to put a line of injection points for a mobile reagent, perhaps permanganate, maybe sodium sulfate, maybe a mobile electron donor, to let that flow into this zone here. So it's located up gradient, but in this case, it's not a barrier. So this is not a permeable reactive barrier. I would consider this a transect of injection points. The difference is how we design it and what the objective is of that. And there's different ways that we can install PRBs, particularly for solid reagents. Trenching is a really great option, and it does create that continuous barrier. That you're just having a straight line of reagent, you're backfilling, groundwater cannot flow through that. With an excavator readily available, but you're limited generally to your depth, 18, maybe 20 feet with a standard excavator, maybe 25 feet with a longer arm excavator. If a PRB needs to go much deeper, on-pass trenching tools are super cool for that, and some of the bigger trenchers now can get to 90 to 100 feet. Anyone ever seen a one-pass trencher? They are massive pieces of equipment. And one of the communities in Cape Cod that we were looking at PRBs on, there were 2 people in the community who were like, one-pass trencher is it's the only way to get a really great PRB. We want a one-pass trencher in our community. And I brought out photos of how big they were. And typically with a one-pass trencher this size, it's probably working side by side with 2 full-size excavators. So this is like the Sail of the Sunset one-pass trencher. But if you show it all the equipment and how big they are, they quickly said, not in my front street. Other methods for solid substrates, I've been involved in some projects in the last year or so, actually looking at auger boreholes. Just an auger attachment on a geoprobe, borehole 12 inches in diameter. We're backfilling them with wood chips and a gravel mixture. This is primarily for nitrate in this case. But what we are is we're creating zones that are much higher permeability than the surrounding groundwater, even if when it is fairly coarse sand. This is even more permeable than that, reducing environments to stimulate enhanced bioremediation of the nitrate. And also looking at, if you kind of think about a bulkhead along the shoreline, there's nitrate flowing through here. There's been some studies where we've looked at putting boxes or wood chips immediately behind a bulkhead. In this case, we can put our reagent very close to the shoreline near the point of discharge. We talked a lot about earlier today, on particularly on injection, and PRBs can be created with injection points as well. These can be with your injection wells or temporary injection points, and they both have pros and cons in terms of drilling, depths, and real pro of injection wells. There's a little less flexibility in terms of your intervals and your locations, particularly if you might need to go back in time, depending on the size of your plume and what your anticipated lifetime of this plume is going to be, where direct push points give a lot more flexibility, but there are restrictions in some of the drilling and the depths. Like, for example, this one on the left here, this is actually a PRB in weathered bedrock, so a geoprobe would not be able to get into that depth. And with injection methods for PRBs, some of the different design parameters we want to be looking at are how close are the injection points going to be with each other? How many rows do we have? So in this case, this was a 3.5 acre plume where we had multiple PRBs. They were spaced 50 to 70 feet apart, somewhat on axis. And each of these had 2 rows. Here's another multi-acre plume where we had 3 rows of injection points. Some of the things we look at when we're thinking about what spacing of the points, how many rows are what are we injecting? Are we injecting a liquid that may also be able to migrate to somewhat a little bit after injection? Are we injecting a solid slurry that once you inject it, it's going to be stationary where it is? Solid slurries, where I would often recommend a closer injection point spacing and potentially more rows. Another key factor is, what is the desired residence time for the treatment that we need? It's not exactly comparable, and a lot of us talking about some of the benefit contact time and the like, but column tests can also give us some of that information. Sometimes even just batch scale bench reactors of just what is the kinetics and how many hours or how many days might we need for the reaction to happen to have our desired contaminant reduction. And then when we think about hydraulic conductivity, seepage velocity, how much time in that barrier, or in this case, maybe if we have multiple barriers, both these cases, maybe if the groundwater is flowing in here, it may take traveling through 2 barriers to meet your remedial goals. And then sparging is another means of PRBs, and particularly it's often set up as a curtain. We're looking to get overlapping circles within our radius of gas distribution. And in this case, just a reminder, it's permeable, it's a reactive, and it's a barrier. So if you have your contaminant plume, it's flowing, and then it's not making it past that. And this can be air, oxygen, or other methane, propane, butane, other organic gases. So looking at some of these side by side, looking at trench, looking at injection points, looking at auger boreholes, they all have benefits and challenges or limitations. The trenching, the best part about it is it's continuous. We can put in solid substrate from really long lasting substrates, 15 plus years with organic wood chips, with 0 gallon iron. And then same thing with the backflow boreholes, longevity if we can have a solid substrate. And one of the great things about the solid substrates here is being able to go near surface water oftentimes. That we're not worried about our injected substrates, we're not worried about an oil, we're not worried about a persulfate getting into a surface water body. But they also do have limitations in their residence time as well. So that's something to kind of offset and where we may need more roads or maybe multiple trenches, depending on what that is. Injection points, typically you can create a larger radius of influence. Quick note, I generally dislike this radius of influence, but larger area around your injection point because it's never really gonna be radial when we're injecting. But, and you have less disturbance for often just having small injection points, but we, often have smaller longevity compared to a solid substrate. So pros, cons, where they can be placed, where they can't be placed, what depths they can attain. But they're all, should be left on the table when you're thinking about your PRB planning. So conditions that are favorable for PRB: access. If there's a place where there is a contaminant flux coming through and you can place a PRB, that's probably a good location for it. We want to be knowing what our groundwater velocity is. Hydrogeology is going to be a continuous theme through all of our presentations today. And that's really important in PRBs as well. And here I say not too fast, not too slow. If your PRB, if your groundwater velocity entering your PRB is very fast, probably north of 2 feet per day, that the contaminants are going to be coming in, and it may also be your non-contaminant target demand. Maybe it's oxygen if you want to anaerobic bioremediation, maybe other terminal electron acceptors. So you're going to have a large flux coming in, but it's also going to require a larger barrier or more injection points in order to get that desired residence time. If seepage velocity is particularly slow, remember this is a passive remedy, so that the groundwater is only coming so much, and your PRB is just going to be waiting there, not really treating a whole lot of contamination, because the contamination is not coming in, and that may be a place where a reactive barrier may not be a good option, and it may be better to have more focused gridded injection points where the contamination is, because it's just going to be sitting there. This gets back into our contaminant flux too, moderate to high. If there's a really low flux coming in, the reactive barrier itself may not have a whole lot of cost effectiveness because there's just not a lot of contamination that it can be there to treat. And we've seen this on some of the other presentations earlier. Also having a characterization, and for a PRB in particular, vertical characterization. Alana mentioned earlier, oftentimes 80% of your mass is going to 20% or less of your aquifer thickness. Here is an example of a site where we had groundwater sampling for nitrate every 4 feet. And we can see here we've got this really nice spikes. We wanted to make sure that our PRB covered this as well as covered this as well. And then above and below, there was relatively low nitrate. So we knew where vertically we needed to put our PRB as well. And we can target that both lengthwise, axis-wise, as well as vertically, where our PRBs need to go. That's where we can be most cost effective in what we're applying. And then unfavorable conditions, this is true for a lot of in situ remediation. If you have above ground features, do you have buildings? Do you have surface water? Are there subsurface utilities nearby? Low permeability soils is going to yield low seepage velocity, low contaminant flux, where for a PRB, you're waiting for the contamination to come into you. And then the velocity, right? If it's too slow or if it's too fast, it's going to be challenging to design an appropriate and effective PRB. So now we said, all right, we want to install a PRB. We have located approximately where we want to put it. The dimensions of the PRB are really important design components. So your length, as I said, it's going to be perpendicular, near perpendicular groundwater flow. We want to locate it where we're going to support remedial goals. Depending on, are we trying to get to low concentrations to protect the receptor? Are we trying to protect a property boundary? And so that does go back into access. Where can you actually place your PRB? Vertically, as I said on the last slide, it's where we're going to intercept our flux. And then the width of the PRB, this is the dimension in the direction of groundwater flow. The key component is providing adequate residence time. We want this to be an effective barrier. We want the contaminants to come in. We don't want the contaminants to go out. So we want to have appropriate reaction time such that the contaminants are not coming in and some of the contaminants are still going out. And we want to account for variations in groundwater flow as well as hydraulic connectivity, which can vary vertically and along the length of the PRB. So touching on some variability within a PRB, just a reminder that geology and hydrogeology are very heterogeneous in the subsurface, even on sites where we think it's relatively homogeneous. This is from a boring log on Cape Cod. We're looking where we typically assume it's beach sands. This is even looking at a 10 to 12 foot vertical interval. And this is just one mooring, but we see coarse to medium sand, very coarse sand, medium sand, but we have to see this is medium to fine. But in between here, medium sand, very coarse medium sand, 6 inches of clay. And then there's this clay seam, which that clay seam is right next to a gravel seam. So we have kind of a couple inches of gravel, a couple inches of coarse sand, a couple inches of clay, a couple inches of coarse sand and silt. So even this is right where, from a boring where we were looking to install a PRB, we're seeing much variability in the geology here. And depending on if this is a contaminant that's mostly flowing through the coarser zones, that's good to know. Or if there's contaminants that this is mid-plume and maybe you've got a TCE plume and more of your contaminants are caught up in the sand and silt and the clay, which Alana showed some examples of that. That's important to knowing where to put your PRB and also what reagents and what dosages as well. All right. Been told that every equation you lose half the audience, especially after lunch, but this is a pretty simple one. I hope most of you have seen this one. Getting into the hydrogeology and how important that is, especially for a PRB compared to even a grid injection. So this is the equation to get your seepage velocity as a site. So it's hydraulic conductivity is K, hydraulic gradient is I, and porosity is in the denominator here. Brad talked about this quite a bit this morning about how much hydraulic conductivity can vary, even if someone says it's a sand, hydraulic conductivity of sand can vary over 3 or 4 orders of magnitude. So imagine this is a foot per day to 1,000 feet per day. So that means your velocity could be off by a factor of 1,000. It's kind of important when designing a PRB and your flux coming in. Your hydraulic gradient, we want to get that from site-specific measurements. We want to have a minimum of 3 wells and a triangle, so we can try to get groundwater flow direction. But even still, groundwater flow direction can be quite squirrely on sites. See here, this site where we're looking to design a PRB, regional groundwater flow was to the top right of the screen, except you can see, look at our groundwater elevation contours here. There are various reasons for that, and I'll show that on the next slide. But when trying to estimate our seepage velocity, these things matter. Porosity is also a measurement that we rarely measure in the field. And we can somewhat estimate it, but one of the things that's a little bit of a safer, porosity varies maybe by a factor of 2 at tops, compared to these parameters, which can vary by orders of magnitude. And then there's always the question on any remediation project of dosage. It's particularly important for PRBs. One is, what is our contaminant flux? That can tell us in terms of stoichiometry, how much reagent we might need. Bench scale testing is another good tool to help us determine how much dosage we need, and affecting dosages, how that might affect reaction effectiveness within a PRD. There's also non-target demand for chemical oxidation. There's other soil oxidant demand. If we're looking at anaerobic bioremediation, there's other terminal electron acceptors, how much oxygen is flowing in, how much sulfate is flowing in. Those are also going to be terminal electron acceptors that are going to consume hydrogen, that require an electron donor to overcome that. And a really, really important question is dosage, overdosing versus underdosing. For a PRB, as I said, one of the key components we want our PRB to last as long as possible. So more reagent typically leads to a longer lifetime. That's great. They also help effectiveness, but then we have to balance cost, byproducts of that, and how close we are. We don't want to go through the whole process of designing this and underdose it, but overdosing it can have issues as well. So that is a balancing act that needs to be accounted for with some of these various parameters. And injection volume, if this is an injection PRB, another really, 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 really important parameter for injection programs is injection volume. Whether it's in a grid or a PRB, increased injection volume results in improved duration and contaminant treatment. That's not debatable. It's one of those things where more reagent, more injection volume, may increase time in the field, it may increase costs, but it is going to increase effectiveness. That's the important part. General rules of thumb, 10 to 30% of the estimated core volume within a PRB. It can be higher can be better, as I said, but that's sort of a range of what I've seen in my experience and have been very effective for generating long-lasting PRBs. But there's a lot of site-specific consideration for that. What reagent is it a solid? Is it a slurry? Is it a liquid? What is the soil type? In very permeable soils, more reagent can get in. What is your depth? If you're injecting very shallow, injecting higher volume shallow may lead to more, potentially could lead to daylight depending on the soil type. That's a concern. Subsurface utilities, we don't want our reagent also getting into utilities, so that's a balancing point in determining injection volumes. And in monitoring our PRB, and this slide's a little more focused on performance, so after the PRB is in, we want to really support the really two questions for most important theories. Efficacy, how well does our PRB work? Is our contaminant coming in and then not going out? Are we getting really good treatment in the PRB? And when the reagent may need to be replenished. We want to have monitoring wells up gradient so we can know what the flux coming in is. And I've seen sites where even there's variability in concentration and flux quarter to quarter. And there's not many sites that also are looking at upgrading concentrations on a quarterly basis, often until the actual remediation happens. Right, we're doing our remedial investigation, maybe on remedial design, maybe we collect 1 or 2 or 3, we install a well, that's going to be upgrading a well, we sample it 2 or 3 times and we do our design. But sampling that continuously over quarters, seeing variability in that, which is kind of neat about what's coming into our PRB. And we want to have locations reasonable distances down gradient. We want to be able to show that our efficacy is working by having a well down gradient, and then maybe also some distances further down gradient as well to look at both efficacy. Is our plume shrinking down gradient? Are there any unnecessary byproducts? Are they going down with distance from our PRB? Of course, we want to look at our chemical of concern. We also want to look at some of the degradation products. If it's reductive defluorination, we can look at carbon. If we're looking at a sulfate PRB, we can look at sulfated sodium and some other reaction products as well. Another reminder, water quality, field parameters, pH, DO, ORP are really, really, really important. So don't forego those. There's a lot of information in there. So a few PRB examples. These are with injection points. This was a multi-acre plume. And although you can't really see it here because it's just a big grassy open field. So this PRB2 here was this PRB here. We created this with a series of direct push injection points. This had 3 rows of points. So we installed those at our sets to have overlapping points and to create a continuous PRB through injection. Kind of see here, this PRB4 is a little bit offset. There was an access issue over here, so we couldn't get, and we wanted to catch the outside of this here. This PRB looks like it's short, but the historic source was right here. So what we knew about, again, capturing flux, meeting remedial goals, this PRB did not need to be as long, even though the flume was created out this wide based on the data available. This is another PRB. This one is in New England. This was one of those sites where here's a forested area. Let's go collect our background sample there to compare. And they found really high PCE concentrations. Oops, somebody did something out there. And so they did some more sampling and actually found 2 relatively high concentration areas, one up here and one in this box here. So what those became is those became graded injection points to meet the objective, knock down the highest concentrations as fast as possible. And then now we are in this forested wetland. We don't want to go in and clear these beautiful pine trees. We don't want to go in and just drive rigs and whatever other tooling in and out everywhere. So plus it's a multi-acre plume. So we went with a series of the source area grids, a reactive barrier, series of reactive barriers, catching some of the higher concentration, and then 2 longer PRBs down towards the south. There's a wetland stream here, which was one of the primary receptors. So it was more for mass destruction here, as well as, because this is a forest, it was not going to be developed. this area was considered for potential development, so we wanted to have a wider PRB across the entire plume and to protect the stream. Combination of direct push points and overburden and injection wells in weathered bedrock with enhanced reductive dechlorination. But again, we're seeing here PRB sizes, depths, widths are being determined based on the contaminant concentration profiles, like spatially, vertically, as well as meeting remediation objectives in different components of the site. So here's a PRB for one of the nitrate PRBs I put in. I can't speak for the krigging, but I really love this image for what a PRB that's effective can be. We can see here out on the west side, high nitrate, 21 milligrams per liter, 7.65 micrograms per liter on the south side. And then on the other side of the PRB, non-detect nitrate, if not less than one, rarely low concentration. So high nitrate in, effective PRB here, and low nitrate or non-detect nitrate. So really seeing the effectiveness of this denitrification PRB. And just as a note, this data was collected 5 years post EVO injection. So this is showing a long-lasting PRB, and it just keeps on humming, doing exactly what we wanted. So again, having a long-lasting PRB is desirable. So just a few lessons learned, and a lot of this is hydrogeologic related. This was the slide I showed earlier. Groundwater flow direction is really important in understanding PRBs. So in this case, we knew groundwater flow direction regionally was to the northeast. There was a surface water body about 200 feet, 300 feet this way. So we had a plan for a PRB. We were going to have up gradient wells, down gradient wells at multiple distances, cross gradient wells. So we could also evaluate potential flow around. We put this whole network in, and we realized that groundwater flow is not exactly following regional trends here. What there was there was a stormwater retention tank here. There was an irrigation well over here, so there was some pulling, but it wasn't operating all the time. Mostly in the summertime when there was a nice baseball field over here. And then there was a municipal leach field over here. So there was actually discharge of water here, so there was pushing more groundwater west to east. So and when you put all those features on, then we can start to see, some more western component here, some northern component here, and some funny shape around the stormwater retention basin. But generally, regional groundwater flow was still that way, and we also ultimately we extended our PRB to have a little bit more of an L shape to capture the nitrate coming this way and the nitrate coming in from the leach field as well. And groundwater flow direction, this was not a PRB site, but I find that as a nice visual, can change seasonally. So this is the same site, groundwater flow direction shown based on groundwater elevation contours in October and January. In October, groundwater flow is still mostly south, but a little bit more southeast direction. In January, it was still primarily south, but it was to the southwest. So when we're thinking about a PRB, an east-west PRB may meet your objectives, but these are just reminders that on really any site, groundwater flow direction is seasonal and can have minor variation, which can affect your remedial design. The number of injection rows are really important, and it really has to do to make sure that we're having a continuous barrier. If you have a single row, it's potential that groundwater could flow between there and not be treated. But if we had a single 2 rows or 3 rows, there's less likelihood for a contaminant to flow through a barrier and not be treated. It also can increase our residence time, can increase our safety factor in there too. And similarly, this is one of the borehole PRBs where we had 2 rows versus 3 rows, and 2 rows reduced the nitrate by nearly 50%. That's great to reduce your nitrate 50% right at the shoreline of what's going in this eutrophic harbor. But the 3 rows of barriers knocked it down to non-detect concentration. So we just saw less likelihood of flow through and probably a little bit more residence time as well. And then one of the questions I said of the monitoring program is when to refresh. When your reagent is consumed. And this can be, you may see this through your contaminant degradation effectiveness is starting to decrease. You may start to see breakthrough of your contaminant where you may have had years of non-detected, very low, concentrations on the downgrading side, on the effluent side, and now you're seeing those concentrations back up. Those are hints that your PRB may need to be refreshed. We can also look at various water quality parameters, particularly for anaerobic bioremediation, whether it's chlorinated solvents, nitrate, or looking at your dissolved oxygen concentration, oxidation reduction potential of electron acceptors. If you had a persulfate oxidation barrier, it may be ORP is now starting to go down on the downgradient side of your barrier. You may start seeing less sulfate. That's just showing that your reactions are starting to wane. A few recommended resources, and these two on the left are older documents, but I still go to these periodically and putting this presentation together. This is the ICRC PRB 5 document. It's from June of 2011. Highly recommend this one if you're thinking about PRBs. And there's a design guidance from a CERTA project from 2000. I spent a bit of time with this, putting these slides together. So I would highly recommend this one. This third one is a newer one. This was through one of our Cape Cod PRBs as part of the grant from US EPA. We assembled a permeable reactive barrier engineering design plan for injection. And this was assembled by ISOTEC along with Terra Systems and the West Lebanon Institute. So just in summary, a PRB gives a wide range of treatment options, whether they're solid, liquid, trenches, boreholes, injection points. Generally, PRBs have a small remediation footprint, which can be really valuable in large plumes in sensitive receptors areas. I showed one that was in a forested area. And it can be a very cost-effective approach for large plumes. Instead of gridding up or doing active remediation across multiple acres, it's possible that you can put a barrier here, put another barrier 50 or 60 feet further down away, and over time, you're going to achieve treatment because your contamination that was continuing to flow and flow and flow is going to be cut off and reacted. So now you're going to put flushing clean water back down gradient of that. And just kind of some of the key points: groundwater flow direction, velocity, vertical contaminant transport, vertically and spatially across a PRB are really critical to your design.
Great.
So that's it.
Minutes for questions, excuse me.
Yeah, back over there.
How do you go about refreshing these after their lifespan?
So injection PRBs are more commonly the ones that require refreshing. They have shorter lifetime, so it can just be re-inject. Yeah, some PRBs are whether it's a well, that could be easy. But if you're anticipating going 5, 6, 7 years between injection points, you may not even want to have infrastructure and just go back with a GeoProbe at that time. The solid substrate ones, I've seen numerous examples for ZVI wood chips, 10, 15, 20 year, but eventually they still may need to be refreshed. And some of those could potentially, for like, if it's a wood chip for reductive dechlorination, you could inject EVO right into the wood chips themselves. And because you already have this barrier, it's more permeable than surrounding groundwater, just put new hydrogen and electron donor into there.
Anyone else?
Do they fail very often hydrologically through plugging or changes in the conductivity, or have you found that they're pretty stable conductivity wise?
So by failing, do you mean like not achieving treatment, or the groundwater is not entering the PRB, or it's just not getting the treatment that you desire?
Not entering because of changes after installation in the conductivity.
Sure, yeah. One of the things, and I'm really keen, and I would have a much better answer for you in about a year. There's a PhD student at Tufts who's just starting, who's really interested in changes in hydraulic conductivity with injection. So he had a senior thesis that was a lot of column studies, and he's looking for some field studies to go out and do some intrinsic hydraulic conductivity measurements before and after. So stay tuned on that. But what the intent of these is not to affect the hydraulic connectivity. So like the wood chips and gravel, those are great because, and one of the other, PhD that I'm working with has done some hydraulic connectivity estimates of wood chip gravel mixes, through column testing and the like, and you're increasing your K value by an order of magnitude maybe, which is awesome, so for PRB purposes. And then I know there's at least one EVO ZVI PRB that I was involved in, where the consultant went out and did slug testing inside the barrier. We had 2 rows of points that were 10, 12 feet apart, and there was a monitoring well somewhere in the middle of there. And I think they had 2 or 3 monitoring wells, and they did slug testing before and afterwards. One well was almost identical, and I think there were 2 wells where, to be honest, the hydraulic connectivity increased by like a factor of 1.5 or a factor of 2. So when you're kind of thinking about hydraulic connectivity being an order of magnitude parameter, if your hydraulic connectivity pre and post went up by, it doubled, you're like, 2 times 10 to the minus 4 or 4 times 10 to the minus 4, we're kind of looking at the same number. And it's kind of, so maybe it went down a teeny bit on your hydraulic connectivity, but it's essentially the same, not a significant decrease. And that one, we have multiple years of seeing our VOCs decrease with that monitoring wells 10 and 20 and 80 feet down gradient.
That's interesting, because normally you think of the granular material or mineral material being more stable than the organic material. So you're not really seeing degradation of the organics into anything significantly different over the time period that.
Right, yeah. I mean, your wood chips are not breaking down to anything that's clogging your aquifer. Your emulsified vegetable oil is not having enough of an impact. Your zero valent iron is not, like, in cases where you're injecting zero valent iron, you're not having enough of an impact on that to change the hydraulic connectivity, at least on a slug test scale. I'm sure if you went out with a Vaughn's flux meter and hydraulic connectivity, maybe on centimeter or 6-inch scale, rent one of those and but even and there was even a clay activated carbon mixture presentation that I saw recently for PFAS, and they also did slug testing too. And maybe the hydraulic conductivity went down a little bit, but it was all same order of magnitude if you're looking at centimeters per second. And that's the intent. We don't want reactive barriers where the hydraulic conductivity is going to decrease, because then you're not going to have a permeable barrier.
Is there concern or consideration for either disposal or reclamation of the barrier if it's accumulating metals or radiologicals or things like that at the end of its useful life?
So I've never been involved in a radiological one, so I think that would be a concern potentially. And right with the metals, that on one hand, is it specifically designed for metals? And if you're doing a barrier for metals, the objective is to prevent the metals from going further. So you kind of assume that they're going to be there. And as long as the conditions, if it's a pH adjustment or creating reducing conditions or whatever their desired conditions are, if that's maintained over a really long period of time, then that's kind of the desired objective, is to accumulate them here to clean up the groundwater and protect some here. If it is let's say we're looking to treat CVOCs and maybe there is an accumulation of metals within that barrier because you're creating reducing conditions or things like that, it's something to consider. And it's really important to monitor for that. I have seen sites where both with EVO injection as well as wood chip barriers, we have seen the iron and the arsenic increase on the down gradient side of the barrier. Most of the time, though, I think all the examples I know of, the arsenic it's gone up, but it stayed below the MCL. So we're like, oh, that's kind of not unexpected.
That's what I was thinking about, was if it's accumulating over a long period of time, does it eventually cause an issue for site closure if it's exceeding a state standard of some sort?
That's a good point, because I mean, and that's true for a lot of our in situ remediation is maybe we're treating contaminant A, but what are the byproducts? What are we also creating in terms of metals and the like? On some of those PRBs, we've seen that the within 50 to 60 feet on most of these sites, your metals are back down to baseline concentration. So they kind of go up within 10 or 15 feet of the barrier, but then if you started putting monitoring wells every 10 feet beyond that, you would start to see the monitoring. So it's a very narrow zone. And I guess we are in the risk reduction business, right? So like what is, you know, is slightly elevated iron and arsenic outside of your PRB compared to high concentrations of TCE coming in or high concentrations of nitrate coming in? You know, I guess nothing's perfect. And I think the best way we can answer that is to not say, I don't know, but to be actively monitoring for this and be thinking about this. And the more of these pilot tests and case studies we have, where we can say, well, on this site we saw this, and this site we saw this. So then on the next one, we can either plan for it with how we design it. What is our monitoring strategy? Or maybe it's just simply, how do we communicate that to the various stakeholders, whether it's the regulatory agency, the neighbor, the community that we're working in.
To follow up on that, and as far as the hazardous waste generation is considered, talk about these barriers have a lifespan. Do you ever have to move the barrier? And if you do, are you generating like a hazardous waste metal type of thing?
Sure, yeah, so I mean, this is actually a hot topic because the Suffolk County on Long Island, New York, is wanting to put in a PRB abandonment plan. So when you put your design plan in, they want an abandonment plan now. And not really sure what, you know, what the lifetime of these are, and some of these we want them to last decades. So will they ever be? But I think it really depends on what your contaminant is. And some of our contaminants, we are looking to degrade the contaminant in place. So we don't want to be accumulating TCE or benzene or 1,4-dioxane in our barrier. We're hoping that our reactive barrier is a degradation barrier and not a partitioning barrier. If you're trying to treat one contaminant and maybe you're creating reducing conditions in your barrier and then metals now become an issue, we may or may not be accumulating those metals. And they may be mobilized from the barrier and they may just flow out. And as soon as they come in contact with oxygenated groundwater, 10 or 15 feet downgrade, they may just precipitate there. So that's a consideration. I think we'd all acknowledge that PFAS is still that big question mark, and barriers are being put in for PFAS. And they are partitioning and barriers to capture them in the near term because we're looking to protect some sort of sensitive receptor. We know it's not a forever, because we're not treating them, we're catching them, and it's possible for them to come out. So might in the near future, might some of these PFAS PRBs may need to be removed, or I think we're all hoping as an industry that maybe we'll have some means of, but you know, time will tell. But right now, the primary objective is to protect this. So if we can protect this from PFAS by putting in a barrier here, that's a good strategy for right now. But they are excellent questions, and it gets back into we should be talking and thinking about these and not going, yeah, I don't know.
Any more questions? 2 more minutes. 1 more minute.
Your nitrate situation you had, would you ever use a secondary substrate with like vegetable oil in addition to the wood chips?
You could. I don't know of an example where they've done both wood chips and EVO yet. But I can see potential where maybe we want to put in some of those columns and then inject through that. So maybe you don't want to put, it's one of the things with the columns, and we're kind of going through these costing on a few projects now, is it's drilling intensive. If you need to get down to 30 feet, you can probably put in 3, maybe 4 columns a day, especially if you're spacing them every 2 feet. So that's a lot of drilling, a lot of time in the field. Maybe there's ways to put in these wood chip columns at a wider spacing, and that's going to have a much higher hydraulic conductivity. So there is going to be some preferential flow into these columns. But maybe if we put if we inject out of that as well, we can get that kind of distribution of our EVO out of the wood chips as well. So we have this really long-lasting wood chip. We get EVO that may fill in those gaps and last 5 or 6 years. And so that's not a bad combined approach. Actually, kind of make me think of that project that I'm working on. So I'll have to give you credit when we eventually, when I'm working on the conference in 10 years, you'll get going.
I'll give you my card.